our principal, faculty members, research scholars, and students for the IEC webinar on Incubation Center IGCAR production. And for today's session, we have Dr. N. Subramanian. He's a senior scientist at Indira Gandhi Center for Atomic Research, Kalpakkam. He is also professor of physics at Homi Bhabha National Institute, Mumbai. He's heading the DA Incubation Center at IGCAR, Kalpakkam, where he's exploring how best to translate lab-based R&D work to industry for meeting the government. The Incubation Center has already transferred 3 spin-off technologies of IGCAR to industries during 2021. So Dr. Subramanian graduated from at Mumbai in 1991, securing the Homi Bhabha Gold Medal, and joined the Material Science Group at IGCAR as a scientist. Since then, he has been involved in investigating the behavior of condensed matter at extreme conditions induced by the application of high pressure and temperature. He received his PhD in physics from IGCAR, followed with a postdoc at Cornell University at USA. He is well abroad for his findings of peculiar melting behavior of solid hydrogen and for discovery of a new form of oxygen that he labeled as phase at extreme conditions using Raman spectroscopy. So Dr. Subramanian's paper, changes in hard fluid hydrogen at megabar pressures, published in the high-profile journal Proceedings of the National Academy of Sciences, is being increasingly cited by several international peer groups that includes Nobel laureates. He has developed several novel techniques to perform the above challenging experiment, and at the Carnegie Institution of Washington, he has set up a facility for doing Raman spectroscopy of ultra-tiny samples under hot, dense condition created by intense IR laser beams. So in IGCAR, Kalpakkam, he has developed a state-of-the-art laser-heated diamond anvil cell-based facility based on CO2 laser, capable of subjecting matter to extremely high pressure and temperature. And his passionate pursuit of the above problems, which led him to collaborate extensively with various research groups both within India and abroad, with universities such as Harvard University, Cornell University, Carnegie Institution of Washington, Argonne National Laboratory, then Hazilab, Petra 3 at Germany, and Photon Factory at Japan. So he has several honors to his credit, and he has delivered more than 25 invited talks in various national and international forums, and he is a recipient of prestigious fellowships from reputed institutions such as Harvard University and Carnegie Institution, and he has also received awards such as DAE Science and Technical Excellence Award, Homi Bhabha Award, and Kalpakkam Science and Technology Award. Since January 2022, he has been appointed by University of Madras as a member Board of Studies in Physics for post-graduation. So we are happy to have you today in our campus virtually, sir. So I welcome Dr. Subramanian, sir, and I request him to deliver the talk. Over to you, sir.
Thank you, Mr. Sere, and it's a pleasure to be with you all today morning. And thanks again for nice words of introduction. It always feels good to listen about oneself once in a while. And so, shall I start sharing my presentation now?
Yes, sir.
Yeah. So I'll present my PPT window. Okay. So, is the presentation visible to all?
Yes, yes, sir.
So, I'll start now. So, I'll be talking for the next 30 to 40 minutes, introducing our DAE Incubation Center at IGCAR Kalpakkam. So the photo you're seeing here is the proposed place where the Atal Incubation Center will be coming up soon. Okay, that's in the Anupuram campus, Anupuram township, outside our high security area. And my office is in Homi Bhabha building in the heart of IGCAR. And my email is subi@igcar.gov.in. Please feel free to contact me anytime. So the plan of the talk is as follows. I'll first go through the basic mandate of DAE, and then a little bit about various spin-off technologies that have emanated from DAE over the past several decades. And then I'll introduce our newly formed DAE Incubation Center at IGCAR. And then slowly I'll enter into other topics such as in explaining the difference between, say, incubation and the technology transfer, because there is still some confusion in the minds of people about these terms, at least within my own colleagues, which I feel I thought I should explain about that. After that, I will explain this concept of what's called how to assess the technology readiness level, which is a basic pointer to the incubation process. And I'll also explain briefly how our incubation center is seeking inputs from technologies from our own colleagues. And then I'll explain the incubation process that we have formulated within DAE and approved by Chairman Atomic Energy Commission. And then I will, like any good lawyer, I will go on to argue how incubation will lead to a win-win kind of a situation for all the people concerned, whether it is the technology developers, the incubating companies, or the academic institutions involved, students, and all of us, including us at the incubation centers. And then finally, I'll just briefly touch upon IPR-related work, which is also part of our responsibility. And then I'll conclude my talk there. Okay. But this is the plan. But feel free to stop me anywhere so that we can interact more on a particular topic. Okay. We don't have to wait till the end of the talk for discussions. So I'll go through the mandate of the Department of Atomic Energy. The main mandate is to provide energy security to our country through a multidisciplinary R&D program in nuclear research. Okay. And as envisaged by Dr. Homi Jahangir Baba, the founding father of our nuclear program, okay, Indian nuclear program will be proceeding in 3 stages to build in this energy security, long-term energy security for the country. Okay. Right now, what we have is a large number of pressurized heavy water reactors that are in operation, and which use natural uranium as the fuel. Natural uranium is about 0.7% uranium-235, which is the most useful component that undergoes fission with thermal neutrons in these reactors. And then about 99.3% it is uranium-238, which cannot be directly be used to produce power. Its neutron capture cross-section in the thermal energy range is very poor. Okay. Still it is 99%. Still we use natural uranium in our PHWR reactors. And with the very limited natural uranium resources in our country, we hope to produce about 12 gigawatt electric over a period of 30 years. And already we are producing close to 7.5 gigawatt electric in our country from these PHWR reactors. The most important thing is from the PHWR, you have produced a large amount of plutonium-239, which also cannot undergo fission with thermal neutrons. So this plutonium-239 and the depleted uranium-238, okay, they are formed as fuels, and they form the fuel for the second stage of our Indian nuclear program. And so these are basically plutonium fueled, what called fast breeder reactors. Okay. So what happens is, in these fast reactors, the fast comes from the fact that this fuel has a good capture or good interaction with fast neutrons. Okay. So they undergo fission when bombarded by the fast neutrons and produce energy, which is ultimately converted to electricity. And with this, we are now in the second stage of the nuclear program. I will talk about it shortly. And this is expected to produce about 300 gigawatt electricity in about 30 years' time. And these are called breeders because apart from the plutonium-239 that is being put in, this depleted uranium from the PHWR that is also put in along with it, which is basically uranium-238, it undergoes transmutation into plutonium-239. So you, in effect, you breed more plutonium-239 than what you actually put in. So eventually, over a period of a decade or 1.5 decades, you will actually produce double the amount of fuel than what you put in. So this is called the breeder reactor. So we already have a fast breeder test reactor in operation in Kalpakan, a 40 megawatt reactor. Okay. And the byproduct, so what we do is in these reactors, the walls of the inner walls of the reactor will have what is called as thorium 232 blanket. Thorium also again does not undergo directly fission, but it can be converted into a fissile material when it is irradiated by fast neutrons. And the beauty is, in our own Manawala Kurchi region of South India, we have plenty of thorium reserves, enough to last for next 500 years. While we don't have uranium, we have plenty of thorium. So Dr. Homi Baba thought about exploiting this huge thorium that we have in our country, and so the second stage of the reactor makes use of thorium as a blanket and converts it into fuel. And this thorium gets converted to uranium 233, which forms the stage 3 fuel for the stage 3 reactors. Okay, these are again breeder reactors because so this we will have more thorium as blankets there, and we get converted to U33 again inside. And with this, we hope to achieve about 500 gigawatt electricity, and it will continuously be working for about 500 years. So we have so much thorium reserves, and this is the basic three-stage program. So in order to achieve this dream of the Department of Atomic Energy to provide energy security to the country, the Atomic Energy Commission has set up several R&D institutions, such as the main one is BRC Mumbai, and then second major unit is IGCAR Kalpakam. Then we have the Raja Ramana Center for Advanced Technology Indore, Variable Energy Cyclotron Center at Kolkata, AMD Atomic Minerals Division or Directorate is now called Hyderabad, and then there is a Global Council for Nuclear Energy partnership in this is actually Haryana, Jasur. This is recently set up institute. So these are various R&D organizations. We also have several public sector undertakings that deliver these products. Okay, NPCIL is a major organization, and etc. Okay, and then we have Bhavini at Kalpakam, which is tasked with the responsibility of setting up India's first fast breeder, commercial fast breeder reactor, or prototype fast breeder reactor, not a commercial reactor. And then we also have several industrial facilities like heavy water board, nuclear fuel complex, which fabricates all our fuels, and then Board of Research and Isotope Technology in Mumbai. We also have a few service organizations to help us run the show. Okay. And we also aid several institutions such as the Tata Institute of Fundamental Research in Mumbai, Tata Memorial Center, Mumbai, or basically Tata Memorial Hospital for Cancer Care. And then various basic research institutes such as Saha Institute of Nuclear Physics, Institute of Physics, and so on. IMSC Chennai, we just have all these institutes. Okay. And this is just a representation of various units of DAE in a single map of India. You can see the huge spread of the atomic energy. And so I'll come back to this mandate again, especially with respect to our IGCAR Kalpakam. So this is we are representing the second stage of the nuclear program. Our fast breeder reactor based on mixed oxide of mixed carbide of plutonium and uranium is working pretty well. It's the 40 megawatt thermal fast breeder test reactor, which was the test bed for designing the more ambitious 500 megawatt electric prototype fast breeder reactor, which is under construction by Bhavini. And so we are pretty much in this. And and the thorium, the Kalpakam also has the unique feature of having all three stages reactor in operation. We have the Madras Atomic Power Station, which is a pressurized heavy water reactor, and we have the FPTR and